All right. Hi, everyone. Today, we're very happy to have Jinzhao Wang from Stanford University giving us a talk about quantum information energy teleportation versus quantum information teleportation. Please.
Okay. Thank you very much for inviting me. Today, I'm going to tell you a story of teleportations. Okay, usually that only just mean one thing, that the very textbook material of information teleportation, or we just call it quantum teleportation always. But today, I'm going to tell you something about another teleportation that's being studied in the literature. And recently, okay, there's some experiments that make people, get back to be interested in this topic again. This is called energy teleportation. And well, of course, so when you have two such phenomena, it's very natural to ask the question of how they are related. So this would be the main topic of today. So this is based on this archive preprint we put out a couple of months ago with Shun Yao. All right, so let me proceed. Okay, so the usual quantum teleportation, which I'm going to call it information teleportation or QIT, in this talk is the well-known protocol that sort of can simulate a quantum communication with classical resource like LOCC and quantum entanglement. So that is to say, even if you don't have an optical fiber between stretched between Alice and Bob that can send genuine quantum informations, you can sort of simulate this resource by just allowing to sort of pre-share some photons in their own labs that are entangled, and they over a phone call and local manipulations, they can sort of simulate this quantum communication. So that's what teleportation is, or that's why people are interested about them in the context of quantum communication. But a natural question is like, can you teleport anything else with this resource? So energy teleportation is sort of the immediate idea one come up with when you think about this question. So it was studied by Hota 15 years ago or something like that. So it is a very analogous protocol that allows Alice to teleport energy, so to speak, to Bob using the same resource, entanglement and LOCC. So yeah, what it does is really like one-line summary of it is like so energy teleportation allows Bob to unlock and extract energy locally that is otherwise inaccessible. So it becomes doable only after Bob learns the measurement results of Alice, which is at a different place. So you use that as hints to extract energy. So I think the original context that Hota studied this problem is probably in quantum field theory or many-body systems. And because you can think of extracting energy being saying as equivalently creating local negative energy densities. So it's in the context of quantum field theory, it's always very interesting topic, like how much you can sort of push the boundary of quantumness to push the boundary of classicality, and to see that you can actually make local negative energy densities. So this is sort of intimately related, and there's some works in this direction as well, like to think about energy teleportation as a way to engineer negative energy densities. So this mostly by Marty Martinez recently. Okay, let me give you a cartoon of how this thing works. Okay, so let's say Alice and Bob they share the vacuum. So here is sort of the energy plot where this baseline is just the vacuum. Okay, so of course from vacuum, if Bob wants to get energy out of it, it's impossible. because any action of Bob would just inject energy to the system. So it costs Bob energy to do that. So you never gain energy from it. But what you can do is to say have Alice to have your friend Alice to expend some energy to spend some energy at a different place. So Alice will do that by just doing a bunch of measurements on the vacuum, and this of course is going to inject energy to the system locally. And then Alice would just tell Bob the results over a phone call. And then Bob will, act accordingly, according to this classical message, X, some unitaries that he can do locally. And if you engineer this, accordingly, there are ways to allow Bob to extract energy out of that. So this cartoon really shows that this is how the energy teleportation works. And importantly, the overall state in the end of the day is excited state, right? So the energy that Alice spends in her measurement is of course, going to be larger than the energy that Bob gained, because the whole thing is no longer a vacuum; it's some excited state. But the point is that if we just consider Bob's local battery, say now he gains some energy, and all he does is to receive some hints from Alice. Okay, so that's a cartoon. So let me be very concrete and look at a simple finite dimensional systems and convince you this really works. Okay, so if we look at just this Hamiltonian, right? So this is a simple Hamiltonian that has the ground state entangled, right? So we will put here interacting term between Alice and Bob, so that the ground state is entangled. And really, the Hamiltonian just consists of Pauli Z's and the Pauli X's. Okay, so that's a very simple Hamiltonian, and you can check that there's not so much a maximally entangled state, but still entangled state is the ground state of the Hamiltonian. All right, so because it's a ground state, whatever Bob does to the system cannot, let's say, unitary actions, Bob will only raise the energy. So it costs Bob the energy to do any action to the system. So now they play the trick of energy teleportation. Alice would measure, say, the X, Pauli X, and this is a measurement that commutes with the terms in the Hamiltonian that concerns Bob. So Alice's action doesn't directly pass energy to Bob, right? Then Alice would send the result of her measurement to Bob, and then Bob, based on this result, will apply some unitaries, which I'm not specifying here, but you can work this out. So this is labeled by U plus or minus. So if Bob gets the plus outcome for Alice, so he will apply U plus and vice versa. And then you can calculate the numbers. So by learning this hint, Bob can extract energy that is of this this number, which is just you can calculate from this example. And in this paper, it's very explicit. Yeah, so this protocol is really really works, and it's been experimentally tested recently, and also nowadays we can also sort of simulate experiments on a quantum processor. I don't know whether you conduct X experiment, but basically it's a verified experimentally verified effect. Right. So that's the idea of energy teleportation. Okay. So yeah.
Question?
Sure.
But in the standard teleportations, when you teleport, say, a qubit or a qubit, couldn't you write a Hamiltonian that mimic the same structure?
I mean, the way I think about information teleportation is really a kinematic thing. So I don't really care about, so okay, maybe I have some Hamiltonian that prepare for me the entangled state if I cool it down. But once I get the entangled state, I don't really care about the energy aspect of it. But yeah, but I guess in this work, we do care, and we're gonna see that there's somehow a tension between if you want to try to do both things on the same system. Yeah. But yeah, I guess for the usual information teleportation, I don't see how freezing it with a Hamiltonian really change the story or make it more. Yeah, I don't see the point of doing that. Yeah. Okay, yeah. So feel free to jump in and ask any questions at any moment. Okay, so I hope this example is clear. Okay, so I have a simple example even. So let's think about a thermal field double state that I guess familiar to most of you guys. But really, let's say infinite dimensions, just a thermally entangled state. So what I mean is that okay, it's entangled state, and the Schmidt coefficient is this Gibbs weight. Okay, so so each side, let's say we focus on Bob, the density matrix is thermal, right? So it's a Gibbs state. And a Gibbs state is what we call a passive state, right? So a passive state so it just says that if you look at the higher energy eigenstate, it has a less occupation number. And this means that any unitary operations by Bob will only sort of amounts to, you can only make the energy of the system higher, right? Because the lower the lower the energy is, the higher the occupation number. So whatever you do with unitary, you're going to shuffle. You're going to make the ordering such that the higher energy eigenstate is going to have higher occupation number. So that would raise the energy of system. Therefore, it's against extracting energy. Okay, so this is what we call a passive state. So however, so now Alice can help Bob by measuring her side of the system, right, and transmit the result to Bob. So let's say Alice would just measure the energy eigenstate on her side, and then conditioned on the measurement outcome, Bob knows exactly what's the excited state of his system. And then he was just simply rotates that vector to the ground state, and that would extract energy, right? So this is just very simple. So it's like, okay, previously without knowing Alice's measurement outcome, Bob is not sure which state is his system in, but after knowing that, he knows for sure he can apply a unitary to extract energy. So in both examples, it's important that energy is never directly transmitted from Alice to Bob. Right? That would be boring. So instead, it's more like Bob unlocks the otherwise inaccessible energy using a key to correlation provided by Alice. And this is the gist of this energy teleportation story. Okay, so that's, I hope, clear enough. And our work, right? So it's just the natural questions. Right now we have the textbook protocol for information teleportation, and we also have the energy teleportation protocol just introduced to you. So how are related, right? Can we do both with one protocol? And naively, we will think, okay, maybe yes, and they should sort of go hand in hand because they just work so analogously. And indeed, we find, right, there are scenarios where you can sort of simultaneously implement both protocols. Both teleportations with one protocol. However, despite the parent similarity, we show that these two phenomena are not only distinct, but there's also a sort of a tension between them. There's a fight between them. So the take-home message is going to be that when both teleportations can be simultaneously implemented with one protocol, we claim there's a competition between them, and this competition can be quantified in various trade-off relations, which I'm gonna tell you about. Okay, so this is the main takeaway message. Okay, so where do we get our intuition from?
Question?
Sure.
It's a trivial question, but can you teleport electric charge, for example?
Yeah, I think so. Yeah, so I think this way of thinking really is not limited to energy. Any charge, if you can basically consider teleport other charges. So I think there's a work by this guy recently. So Ikeda. If you look at his papers, there's a recent one this year where he studied the same protocol for other charges. But I think, yeah, so energy is just a prototypical example where this goes beyond information. And if you think about, your thermodynamic relation, you have an energy term, you have an entropy term, you have an angular momentum term, you have other charge terms. For anything that appears in a thermodynamic first law, you can think about whether you can play this game. Yeah, I think that's absolutely correct. Yeah. So he wrote a paper about this. You're welcome to check that out. Okay, so yeah, so where we get our motivation from is the setup where it's not, it's not really your conventional textbook teleportation, but a sort of more exotic version of teleportation. Some people like it, some people don't like it. I hope you like it. Anyway, so I'm gonna spend maybe 10 minutes discussing this motivation example, and then before we go to our main results. So it's a, like I said, it's an exotic version of teleportation, and it's discovered to be it sort of happens in holographic contexts. And I think the upshot of this is that there's a dual bulk description of it, where you can think of teleportation as just a very convenient story of a particle falling through the wormhole. Right, so concretely, we can think of two SYK systems sitting in different labs, and they're entangled in some thermal state, and at low energy and large n, they are duly described by a two-sided black hole in J gravity, so in one extra dimensions. The wormhole can be made traversable. So this is just so far on paper. You can just turn on some deformations, some interactions that couples the two distant laboratories of this form, and then you can show that this work corresponds to a shock wave injected into the bulk, and that will shift the horizon such that a messenger that was previously causally disconnected, so the two causally disconnected patches will become connected. If you're sending a particle from the past on the other side, it will land in Bob's laboratory in finite time, because thanks to this shock wave inserted by this deformation. So this is the calculation you can do, and this is the calculation that this guy did. But why we can think of it as anything to do with teleportation, and the reason is that we can think about, really we can map everything to the resource we need for quantum information teleportation protocol. So now we have the resource state is just going to be the thermal entangled state. So that's play the roles of the Bell state. And then the double trace deformation is really can be thought of as a LOCC. right? So what I mean by that is that, of course, this double trace deformation is a global unitary, right? It's not really a LLCC by itself, but you can rewrite it as by rewrite you can write a LLCC protocol that would have the same effect on the Bob's laboratory, but different effect on Alice's laboratory. Right, so you can sort of think of this as a measurement done in Alice's laboratory, and through a phone call, Alice will tell Bob the result, X, and Bob will do some unitary action according to the measurement outcome. So there exists a LACC protocol consists of the measurement and then the conditional unitaries, such that the effect on Bob's lab is the same as the double trace deformation I showed you, the joint unitary. And in this sense, we say that this double trace deformation can be replaced or treated as a LCC as far as Bob's system is concerned. Okay, of course, on Alice's side, it's going to be very different, whether she does measurement or is acting by a joint unitary. But we don't really care about what happens to Alice's side after the moment she sends the message. Anyway, so then the final right. So sorry, the Bell measurement procedure is replaced by the simple measurement but time evolved, right? So you can think of the Bell measurement being something that is sort of it does the heavy lifting, and is sort of some more complicated version of a measurement. And here this is done by the chaotic evolution of the system. So if you do some simple measurement at time 0 and time evolved back, it would amount to a measurement that is complicated. So this is all the components. This is how the components, essential ingredient in a standard information teleportation protocol, get mapped to this protocol.
Question?
Yeah.
So in this example and the example of the TFT that you mentioned earlier, what played the role of energy density or local energy was the modular Hamiltonian. Is this right? That's how. Is that a guiding principle we should have in mind when we talk about?
Yeah, I think so. Exactly. I'm gonna comment on the energy aspect soon.
Oh.
Yes, but essentially yes. Right. So our observation, maybe a trivial observation, is just that, before it's a QIT protocol, it's first of all a energy teleportation protocol. And why is that? Because by the virtual fact that it's a thermal field double state, right? So without Alice's message, Bob cannot extract energy from using local unitaries from the state. So it qualifies, the state itself qualifies for QET. And then we know that, there's a very fact that the deformation injects a negative energy means that, through this action of Bob, he would actually, extract some energy to his local battery, because the system is, the very action lowers the system, lowers the energy of the system. So this negative energy shockwave does two things. Only opens a wormhole, but also sort of allows Bob to extract energy to his battery. Okay, so we can do some calculations that sort of compares the energy change before and after the double trace deformation to sort of quantify how much energy is really extracted by Bob, and this we denoted as E naught, which is really just the negative of the energy change of the system. So this is some Schwarzschild calculation that you can do. The formula doesn't really matter for the story of the talk. All you need to know is that this is just some number that sort of changes with time and also depends on temperature, and maybe most importantly, the heavier the weight of the deformation operator, then the more energy you're gonna get. So this just to show that we can be very concrete about how much energy is changed the story. Okay, okay,
Sorry.
but yeah.
Your formula, this energy falls off exponentially fast with time.
Exactly. So this time would it has some peak, right? So I don't expect this protocol to be very good, either for energy teleportation or information teleportation, because somehow the protocol, the emphasis of the protocol is to have a bulk picture, so I don't expect to be any good. Yeah. But the important thing is that somehow, whenever in the regime we have a bulk, there is a manifestly simple reason where there must be a competition between how much information you want to teleport or how much energy you want to teleport. So this is the main point we want to focus on. But overall, given some of your double state into distant labs, the best protocol to either do information teleportation or energy teleportation is not going to be the traversable wormhole protocol, right? You just do your Bell measurements and that's the best thing to do. Or for energy teleportation, you just ask Alice to measure the Hamiltonian and tell you the result, and Bob will, rotate back to the ground state, as I showed in the previous example. So this protocol is far less from optimum, and therefore you don't see a good behavior of it. Right. Okay. So yeah. So the why we want to study this is because we can sort of see a trade-off in this in the bulk picture. So okay. So let me first complete the story. What I just tell you is the E naught, right? So E naught is just the energy teleportation that you have from this double trace deformation. But remember, for the information teleportation protocol, you also insert you sort of insert a messenger particle in the past, right? So this also has some energy. You need to account for that. So this is gonna let's say the energy of the messenger is denoted by E prime, and it's going to be some positive number. So the total energy teleported that received by Bob, because of the E prime contributes positively to the energy of the system on the right, Bob is going to have less energy than he could from E naught. So the total energy teleported is going to be E naught minus E prime. And we consider a semi-classical regime where this mass of the particle should be very small. So in order to not have a large back reaction. So in this regime, we can really think of this just as a sort of a little perturbation around the E naught. And if we put a delta E on both sides of the equation, you would have like E prime is really the minus delta of E. So we can think of really, let's say we change the conformal weight of the messenger particle insertion, and how that, if we dial that number, how much less energy that is teleported. So we can do this. We can do this dialing. And in the bulk, we have the Birkenstein bound, right? So the Birkenstein bound, as Nima commented, in this context, just really reduced to the relation between the let's say the entropy and the modular Hamiltonian. But on the physics of it just says that it always costs energy to send information, right? So this E prime, we know it has to be positive in order for it to be able to carry information, and we have this bound says that the entropy, that let's say the logical information that it can be carried by this particle is going to be upper bounded by the temperature times E naught, right? So the E naught is roughly sets beta E naught sets the upper bound, sets the Birkenstein bound for how much information that can be transmitted. And there's quantum field theory calculation shows that by, let's say, increasing the number of species, if we use the species as logical code words for the information we want to send, this bound can be well saturated by just tuning up the number of species. Or more rigorously, you can try to calculate, let's say, the capacity, the quantum capacity of the wormholes. And there's some upcoming work by Zhenbing Yang and his students working on this problem. But what I'm trying to say is that this bound is not only, it can be a tight bound. So it's something that you can achieve from the bulk perspective. Right. Okay. So yes.
So based on what you said, is the positivity of relative entropy, that inequality you've written down, gonna turn into the trade-off between, is that what the idea underlying?
Yes, yes, exactly. So it's going to be even the equality. Let's say the right. So I think on the next slide.
First law.
The first law, yeah, exactly. So you're anticipating, yes. So in this context, it's nothing but the first law of entanglement dynamics, right? So it's this equation essentially, right? So we call this like a perturbative trade-off relation. It just asserts the simple fact if we want to send more information, then you need to send more positive energy, and it acts against energy teleportation. Simple as that. And this, it just simply consequence of Birkenspan or first law, as Nima commented. Okay, so okay, does this give us the motivation? Okay, we should really see if this is a general story behind this kind of trade-off relation. Of course, we should look for something that's much more general than this equation number 5. Because it's only perturbative, right? So you cannot say you vary the weight too much because you want to keep the semantic constant description. And also, it lacks universality, right? So this only concerns this particular subset of LOCC schemes that you can study. That the main point of the traversal wormhole is to consider this very special subset of schemes where you have a bulk description, but in general you don't care about that. So you could ask among all LOCC protocols, could there still be a trade-off, right? So that's why we're going to move to a more QI study where we just put everything in finite dimensions and study this problem. Okay, so before I do that, are there any questions?
So there's something I'm confused about, but feel free to postpone it to later. In the story that you told, it was important that your states were passive.
Yes, because I want Bob to not be able to get energy before getting Alice's message. Yeah.
But then the first law is the first law. It's always valid. So I guess the interpretation of energy teleportation is tied to the fact that, I'm kind of confused actually. What is the passiveness condition in this?
I see. So the passive, so the passivity comes from the fact that it's a thermal state. I just want to compare the energy change before. So Bob is gonna so Bob is gonna be able to get some energy only after he learns X. So that's the so otherwise, if the system is not passive, you could say, okay, you could just without knowing Alice's message, you could get energy already. So that doesn't really count as teleported energy. Yeah.
No, I understand, but what I'm asking is that passive versus not passive is about do you order the Schmidt coefficients in your
You order them against the energy. Yes.
Okay, so basically that is the physics of it. But okay.
Yeah, basically that's the physics of it. Yeah, I will as you will see later, there's some interesting story about passiveness and what we call the completely passiveness. So that means we take many copies, still may remain passive or not. But I will come to that later. Yeah. Okay, so in finite dimensions, we're supposed to have better control of the analytic tools we can use to analyze more general LLCC protocols. So that's why we want to do that. Okay, so as a first thing to do, we just translate everything we had before to finite dimensions, right? So we're gonna still consider a thermal state that are thermal entangled state. And the thermal entangled state has in itself a temperature beta that parameterizes the state. And we're going to consider teleportation protocols denoted by some measurement on Alice's side and some operation, unitary operation by Bob. So the picture is just like this, right? So we have we have some thermal entangled state between Alice and Bob, and Alice is going to have some message A prime she would like to send to Bob, and the common trick in quantum information, so instead of saying you teleport any unknown state, you just say that you teleport part of the entangled state. If the entanglement is preserved well, that means the information is sent. Okay, that's just the usual thing you do. And of course, we are sort of greedy. We want something else. We want the protocol also somehow helps Bob to gain some energy in his battery. So that's the energy teleportation part, right? So we will ask, if you want to achieve both things, like what's the trade-off between them? Yeah, so we're gonna focus on teleportation protocols with rank quantum measurements, right? This just generally because it's technically easier and also conceptually, higher rank cross-operator measurements, they just mean something with causal resolution. So since we're talking about the ultimate limit tension or the competition between these two things, we want to focus on the measurements with highest resolution as possible. So we're gonna only study rank 1 projective measurements, not any POVM measurements. Yeah. Okay, so the figure of merit, like I said, in this setup, we can just use or essentially entanglement swapping setup, right? So we can just check for information teleportation how much entanglement that is preserved between R and B, right? So because after this measurement, the A system is projected out, the rest system is projected out, right? So what you left is some state on B and R, and the entanglement in it will quantify how well the information is teleported, and also the energy teleportation side is just simply how much average energy that is gained by Bob, right? Averaged over the measurement outcome probability, right? So you just compare these two things. Yeah, okay, so this is the setup. All right, so this is our first theorem. So it says that, okay, so for a thermal entangled state considered in the previous page, and then and the Bell state which has the logical information or the information you want to teleport on the A prime side, we consider any teleportation protocol, and they are going to be subject to this bound, which just simply says that yeah, the information teleportation together with energy teleportation overall, their performance is bounded by the entanglement, how much entanglement you had in the state, right? This is very intuitive because that's the sort of total resource you have. You can choose protocols that does maybe information teleportation better or energy teleportation better, but they are going to be together subject to the how much total resource you have, right? Yeah, so okay, so both are sort of expectations over the measurement outcomes, right? So this is the statement, and you can see this is sort of very thermodynamic kind of a statement, right? So it concerns energy entropy and they're related by this temperature. And some remarks. So if you want to do the optimum information teleportation protocol, you're just going to do the Bell measurements, right? So that's going to sort of saturate the inequality and set the second term to be 0. Or you can do the opposite. You can set the first term to be 0. And this is just the energy measurement protocol, which I mentioned in the previous example. And however, that doesn't quite saturate the bound, right? So there's a sort of a shift by the equilibrium free energy somehow. Yeah, it's not quite as tight, but you sort of see that you can sort of tune your protocol to do either QIT better or QET better. So this is how this result says. And yeah, the derivation of this result is really straightforward because the state is very special, right? We pick a state that's sort of already have the temperature in it, and just some simple manipulations and keep track of how energy and entropy changes in the system, you will get this bound. So, but the result is sort of also intuitive. Right? We sort of expect this kind of statement to pop out. Okay, so now I'm gonna move on to the more general story, right? So the thermal entanglement state, right? Maybe this is somewhat special. In reality, we would like to say something about an arbitrary entanglement resource. So that's shared between Alice and Bob. So what can we say about that? So the first difficulty is that, if we want something like this, right, it's just essentially a thermodynamic relation, right? So then that means that we need a, sort of a conversion number that tells me how do I change between, like, it's an exchange rate, right? If I want to change between energy and entropy, they are not on equal footing. I need some notion of temperature. But that was provided in the state for me in this case. But if I just consider a general resource state, where should I look for there's such a beta, right? In my setup, I don't have a thermal bath that sort of somehow put my system in some temperature. So I really need some sort of effective temperature that helps me to get such a statement. Okay, so we propose that a meaningful choice is the following. So we're just gonna, so this equation here, it just sets the temperature by saying, I want the temperature such that the thermodynamic temperature on the left-hand side is equal to the entanglement entropy in the state. Sorry, yeah, the thermodynamic entropy equal to entanglement entropy. That's what it says. Notice that this is somewhat different from how people usually pick the effective temperature, say in the study of thermalization, right? So in the context of thermalization, usually the effective temperature is set by equating the equilibrium energy to the energy of the initial state, say. And now we're not doing that. In this context, we set the temperature by equating the entropy. So this is how we pick the temperature. And now you might ask, okay, what on earth does this number mean, right? Like why do such a kind of strange choice? So operationally, this number shows up in the following task. So you can think of let's say if I have many copies of some state rho, and it has some Hamiltonian hedge, I can ask how much energy I can extract it out of it in the asymptotic limit of many copies. Okay, so yeah, so this so the Hamiltonian here is really the n copy Hamiltonian. You just replicate your Hamiltonian n times. So it's like it's a sum over n terms where each term is just to have the copy of original Hamiltonian on the i's tensor factor and identity everywhere else. Okay, so this is what this Hamiltonian means. So this expression has a number sometimes called algotropy, and it's in this case it's the regularized algotropy because we look at the limit of many copies and divide by n. So without this limiting procedure, this is just called algotropy, right? So it's like by unit reaction, how much you can lower the energy of the system and sort of extracting energy out of it. And notice here we don't have any sort of teleportation kind of scenario. You're just talking about a closed system and you want to do something, do unitary action with it. You ask how much you can lower the energy of the system, okay, in the limit of many copies.
So this U is any unitary on the n copy over space?
Yeah, any unitary on the n copy. So it doesn't have to be factorized. Yeah, the joint, it can be joint unitaries across n copies. And yeah, so this is definition, and magically this equals to some relative entropy. So
Oh, okay. Yeah, I was about to say, okay, yeah.
yeah, exactly. Okay, right, yeah. So this is where the temperature shows up. So this becomes some sort of free energy, if you like, for this temperature, right? So in the first argument, you have your original state in consideration, and in the second argument, you have the thermal state at this temperature, which was defined by this equation. Okay. All right. So you can think of this statement as saying, yeah. So beta is really a number that shows up in the thermodynamic limit. And in this context, the only notion of the thermodynamic limit is if n goes to infinity. Right. So that's the relevant notion of thermodynamic limit. And this sort of suggests that if we want to look for a sort of similar kind of trade-off relation for in the context of QET against QIT, then we better sort of consider many copies of the state, right? Because in this limit, we're gonna have a hope that this number will be relevant in the spirit of this result. Yeah, so really this comment here should really apply to the previous slide. So this Hamiltonian consider is H here is really the n copy version of it. Okay, so yeah, that's why we motivated by picking this temperature, and this result tells us we should consider many copies. And therefore, we interested in how the energy teleported per copy is competing over the integral resource with the information teleported per copy. So this is going to be the context of our next result. So let me give you a comment. So this result sort of is kind of interesting. It sort of says that if rho is passive, it could still be, right? So as long as rho is not thermal, if rho is passive, it could still be that when you give you multiple copies, you can still suddenly be able to get energy out of it, even though you cannot get energy from a single copy of it, right? Because this equation says you're going to be some positive number in the end of the day. Right? So you can imagine if your weights, if your occupation number or the Schmidt coefficient are not exactly ordered according to the Boltzmann weights, when you tensor them, at some point the energy ordering and the they are not going to. The ordering is going to be shuffled up at some point when n is large. So this would give you the ability to pick the right U to gain energy. Yeah. So yeah, okay. So but for us, it's important. It's an important point to notice because we wouldn't want to count this energy to be teleported, right? Because this is just something that you happen to be able to do yourself with many copies. So we need to subtract this contribution from Bob's total energy extracted with many copies. So we're gonna have to be a bit more careful about what we mean by the teleported energy in our next theorem. Okay, so this is the main result. We say that if we have now many copies of some pure state, so rho AB is some pure entangled state shared between Alice and Bob, and again you want to send some information that are of this form and copies, and then we consider any teleportation protocols that can, apply joint measurements on these many copy of the systems and joint unit reactions that try to retrieve the information or energy. They are going to be subject to this this bound, and here the SREG simply means that it's the it's the per copy entropy. Taking the expectation over the measurement outcomes, and the energy ERAG, delta ERAG, is basically the expectation value of the energy gain per copy again, with importantly the logotropy term subtracted, right? So this was the last comment here. We would like to subtract the energy that Bob could have just on his own extract without Alice's help. So that doesn't count as energy teleportation. So we subtract that part off. So what's left is genuinely due to Alice's message, due to Alice's help. So then this part together with the information measure, they're going to be bounded by the total entanglement you have in the state.
Sorry, just a quick question.
Yeah.
Is there any way of writing this 10 only in terms of relative entropies? It looks like, is it the inequality that involves 3 relative entropies, or what exactly is?
I would say that yeah, so in the derivation we use different sort of relative entropies. Like so for example, we use the max relative entropy and maybe the smooth version of it, so to prove this result. But in the end, yeah, in the end we sort of want the term to look like this, because we want to, say it's sort of really a computation precurity and QIT. But yeah, I guess you can massage them so that this whole equation just some statement of relative entropy. But I need to check my math and see how that.
You said that delta ERAG is just a relative entropy.
Yes. Yeah. Delta, well, this ERAG is, and yeah, this ERAG is a relative entropy. But delta ERAG. So with this term, I'm not so sure.
I see. Okay.
Yeah. This ERAG is, yeah. Okay, so yeah, so you see that this temperature is what plays the role of the thermodynamic temperature in this thermodynamic relation, and we expect that to pop up at log n, yeah, and that's exactly what we have. Okay, so let me yeah, in the final 5 minutes, maybe just tell you what like how to interpret the results. So the first explanation we can provide is sort of some operational explanation of why we expect such a trade-off to be there. So for information teleportation, right? So as you learned maybe from classes, a good information teleportation really hinges on the fact that you have no leakage of information, right? So if your information leaks to the environment by virtue of non-cloning, they are gone, right? So you cannot get them back. So as to have no leakage, you better make sure you sort of wire up the correlations between Bob and the reference system as neatly as possible. No one else should have any correlation with that system. So this is what you need for good information teleportation. But for energy teleportation, you sort of want some sort of contradictory goal, because you want a measurement that sort of reveals some information that pertains to the Hamiltonian, so as to instruct Bob to extract energy. Right, just like we saw in this previous example, Alice would want to measure the Hamiltonian so as to tell Bob which sided state it is. And that procedure essentially would reveal some information about the system. And naturally, you cannot achieve this simultaneously. Yeah, so these goals would contradict each other, and you have to compromise when given limited resources. Right, so okay, so here's maybe a more physical explanation. So we can sort of rearrange that. So let me just take the statement in theorem 1, which is just the thermal state example. We can just rearrange the equation we have just by putting all the energy term to the right-hand side. And here we sort of say that we can introduce this Emax, right? So we just the total energy in the state. This is sort of also the maximum extrapolable energy you can have, assuming, let's say, the Hamiltonian has the ground state energy 0. And then the upshot of rewriting the trade-off bound in this way is sort of a manifestly like sort of a Birkenstein bound. It looks like a Birkenstein bound. But now we should really understand the energy cost of sending information as the energy deficit up to this log z shift as the energy deficit that Bob could have gained had they used the optimum QET protocol, right? So this is the gap that you lose if you choose to send information. If you use the optimal QET protocol, you could get much more energy. So as Birkenstein himself would argue, it always consumes energy or positive energy to transmit information, and this acts against QET. And in this very concrete context, we see that the energy cost is not sort of explicitly consumed, but it's sort of counted as the part that's given up, right? It's very much like the opportunity cost, right? Because you choose not to do this, therefore you give up some energy that you could have gained, and that's the cost you pay. Right. So in this, if we formulate things in this way, then this is really the same principle as we saw previously in the bulk picture of the traversable wormhole. Right. Although in this here we have a sort of more finite dimensional context where we don't really say, oh, okay, we have a Birkenstein bound proven for us, but I think the essential principle is the same. Okay. All right, so let me just summarize my talk with this picture. So what I'm showing you is basically this plot. Okay, so we have two axes. The vertical axis corresponds to the information aspect, right? So I want to send information with my teleportation protocol, and the horizontal axis corresponds to the energy aspect. I want to send energy. Okay, so our bound is essentially the red line. Right, it says that, okay, depends on how much entanglement resource you have in the first place, there's some converse bound that you cannot go beyond, right? So as I sort of told you before, the traversable wormhole protocol is really suboptimal, right? The point there was to have a bulk description that tells you a nice story, but not so much as sort of doing well in this plot, right? So the traversable wormhole may be somewhere very down in the left corner. But you could ask the question, what about the achievability part, right? Like really, what is this dashed line, which we call again using economic analogy, what's the Pareto frontier here? Like how much you can push the achievable region to our bound. We already know that for the horizontal axis, there's sort of a gap. You don't quite be able to achieve the bound we have. So maybe we can try to maybe get a better formulation of the bound, but we sort of choose our bound because it looks nice as a simple thermodynamic relation. But if you're willing to be more sophisticated in formulating a converse bound, I'm sure you can do better. And yeah, the ultimate question is what's the exact achievable region for all protocols, right? So here, the gray sort of shows all achievable protocols. Like for every protocol, you have a point in this plot, yeah. So I think this is sort of interesting question. All right, so that's all I have. Thank you very much.
Further questions?
maybe a naive question, like, suppose you have a Hamiltonian that has a parameter, and you could have a critical point, for example. So if you change the parameter for different ground states, you will be able to teleport more or less energy.
Yes.
And so naively, one may think maybe at the critical point is where you can teleport more energy. I mean, it's something like that studied.
Yeah, so I think, well, so from what we saw today, like essentially you want more entanglement resource. So yeah, if there's a study of how entanglement changes with at this criticality, then naturally you can also think about doing this both protocols better. Yeah, but I'm not aware of the exact story there.
Thank you.
Any other questions? I do have a naive question.
Yeah.
So the wormhole story you were telling
Yeah.
had notion of dynamics and time, right?
Yes.
So
Yes.
we talked about the amount of energy that's teleported as a function of time. So
Right.
at the end, in your quantum information story, you found some sort of a, some sort of a trade-off between energy and information.
Yes. Yes.
There's another trade-off, which is time-energy uncertainty relations, if you're talking about dynamics of systems.
Yes.
Very high level, is there any way of, are they related? Are there things that one can say? I know it's a very big question.
Yeah. I'm not sure. So I think yeah. So there is maybe not so much related to this work, but I think it's true that people have been trying to put uncertain relation on more precise formulations in terms of entropic uncertainty relations. And I think for the energy time one, there are some efforts in I think I remember one in terms of Fisher information, and another one maybe in terms of entropy, where people try to constrain time measurement, the information containing a time measurement and information containing an energy measurement, like up or bound them by some quantity. I'm not sure how relevant those results are to this story. Essentially because I think the dynamic aspect of the traversable wormhole story there is really, I think of the role of the chaotic evolution is try to mimic this Bell measurement thing, right? So in the end, I still think of them as sort of as a kinematic story. But yeah, maybe that aspect could offer something new to these results. I have, but haven't thought much about it. Yeah, but thanks for the question. Yeah.
Any last questions? If not, let's thank the speaker again.
Thank you very much. Yeah.
Thank you so much for the great talk.
Okay. I hope